Hello and welcome everyone. Welcome to today's webinar on multiphysics for first time right 3D printing. My name is Ajay and I'll be the moderator for today's session. For today's webinar, we have a guest speaker, Dr. Raj Tyagarajan of A2A Scientific Technologies. A2A Scientific Technologies is a COMSOL certified consultant. So Dr. Raj Tyagarajan, he's a successful technology and innovation leader with 25 plus years of global industrial experience in multiphysics engineered product development. Dr. Raj is an alumnus of Cranfield University in the UK and from IIT Bombay. He is also credited with many patents, publications and excellence awards. Dr. Raj is currently growing A2A into three verticals, that is A2A Scientific Technologies, A2A Software Technologies, and A2A Smart Technologies for multiphysics CAE, engineering apps, and 3D printing respectively. Their multiphysics CAE expertise helps industry to solve complex engineering problems and also offers comprehensive CAD, CAE, and CAM solutions to its clients. I would also like to mention that A2A Scientific Technologies has topped the list of 25 most promising engineering consultants in India. This was a recent survey that was carried out by the Consultants Review magazine. So hearty congratulations to Dr. Raj and his team for this great achievement. So coming to today's webinar, today's webinar will be for an hour with the Q&A session towards the end. If you have any questions or comments, please feel free to type them into the chat box that you see at the bottom of the GoToWebinar panel. We will try to take up as many questions as we can during the Q&A session. If anything is unanswered, we'll definitely get back to you via email after the session is over. So now I'd like to hand over the presentation to Dr. Raj for today's topic. Dr. Raj, over to you.
Thank you, Ajay. Thanks for the introduction. Good day to you all. Let's get started with the 3D printing webinar. It's my pleasure and privilege to present this webinar on 3D printing to this great audience. "3D printing is projected as the next industrial revolution, and it can potentially impact each one of us. For CAE expert, it is a dream come true, wherein 3D printing allows you to touch and feel your designs right at your desktop. For an individual, 3D printing transforms ideas into real products faster." After the introduction, we shall look into CAD, CAE, CAM or product development, in-depth technical look into 3D printing, and multiphysics CAE modeling of 3D printing. "3D printing is an emerging technology, and hence you will see a lot of growth activities, different terms and definitions. Hence we shall follow definitions of ASTM committee throughout these presentations. 3D printing is about fabrication of objects using the deposition of materials using a printhead. 3D printing is actually more than 2 decades old technology. The foundation comes from rapid prototyping, CNC, robotics, and material processing technologies. Current excitement is due to current excitement is due to the technology maturity, open source hardware and software, advancements in CAE, history-free card, makers community, availability of low-cost printers, material innovations, low-cost laser, all that propels 3D printing into an exciting future and possibility. We will look into the following are some key benefits of 3D printing: faster and low-cost product development is a constant need in an industry. Customization is customization for consumers with the current mass production technologies is very difficult, but 3D printing enables low cost and custom made. Most of the current manufacturing methods are top down. It's a subtractive process, but 3D printing is an additive, bottom up manufacturing method which is close to nature, where nature builds atom by atom. Here in 3D printing, we build layer by layer close to nature. This is projected to spearhead disruptive business models. Currently, simulation-based product development is successfully leveraged by the industry for faster concepts to marketing of products. The components of virtual product development are CAD, CAE, and CAM. Right side what you see is a new vertical wind turbine concept. The design is counterintuitive, and the fabrication is also complex with conventional process. But with the simulation-based product design coupled with 3D printing made this a reality within few hours. There are many real-world examples wherein, for example, in one example, Siemens turbine maintenance cycle time was cut from say 44 weeks to 4 weeks. 3D printing is successfully used for full-scale automobile, aircraft parts, biomedical prostheses, and many other prototypes. You all are familiar with CAD, CAE, and CAM. But CAM, computer-aided manufacturing, is known to us in different flavors in recent times, like rapid prototyping, 3D printing, additive manufacturing, direct digital fabrication, and solid freeform fabrications. As we move forward with the 3D printing, we will use 3D printing for general use and additive manufacturing as for technical use. Industrial product development is a long cycle process. For production planning, from product planning to concept design to final design to pilot to mass production is a high resource consuming process. This graph shows you the new product development activity, management influence, design cost change over the product development cycle. The cost of design change increases exponentially with the product development cycle, as shown in the green curve. You can see that most of the product development, 80% of the cost is committed at the early stage of the product. Once you set the project rolling, the management influence or control reduces over time, as shown in the red line. So it is imperative that the product development is first time right. This slide shows design change cost for the products. The cost of fixing a defect or a design flaw increases exponentially with the product development. Depending on where the defect or the design flaw is detected, the cost can go as high as 10,000 times of the product development cost. All this emphasizes the need for first time right product development. We shall focus on the multiphysics CAE plus 3D printing for the first time right product development. This slide shows the product development cycle in a simulation-based product development environment. The product development moves from ideas or concepts to CAD, to CAE, to CAM, and to the final product. The red line shown on the top right shows the typical sequential development process, which generally leads to product development not meeting the CTQs. It is better to avoid these kind of sequential product development even within the computer-aided product development environment. The green line at the bottom is a concurrent development process with a feedback loop within each stage to ensure that the product development meets the CTQs. You can see from the concept to CAD or CAD to CAE or CAE to CAM, there is a constant feedback loop so that at you go at the end of the product launch, it is successful. It meets all the CTQs. The concurrent route is the preferred for first-time right product development. In this, you will see CAE is used extensively for product design, which are familiar, process design, manufacturing process design, performance analysis, and even virtual testing. So you can do the real testing virtually. Also, now we do more of even virtual 3D printing, so that we do all these at CAE to meet the CTQs or make the product first time right. "3D printing is nothing but a conversion of concept into physical product. At the concept stage, this graph shows from concept to movement of 3D printed product. So what are the steps involved in a 3D printing? At the concept stage, they start with 2D sketches or drawing on a paper or a computer. The next step is to move this into a digital environment. So this 2D information is digitized into a 3D CAD model in the CAD environment. We can use any CAD software to develop these 3D models. So once you develop these 3 models, we usually use IGS or stuff files as a typical exchange file format for CAD data exchange. Once we have the CAD file, then we use the CAD model is then meshed with the triangles of the 3D model surface known as distillation process. This is usually written in STL file. This STL file is further used to, this information is then used to slice 2D layer by layer data for 3D printing. This is usually written in machine readable forms, for example in G code. This information is passed to the 3D printer, which can read this input and then deposit material layer by layer to build the 3D product parts in any material you want, depending on the printer you choose. This slide shows a summary of classification of current 3D printing or additive manufacturing technologies. This is categorized into 7 technologies based on the manufacturing method which is employed, like photopolymerization, material jetting, binder jetting, extrusion, powder bed fusion, sheet lamination, and directed energy deposition. In photopolymerization, the liquid photopolymer is cured by an electromagnetic activations, electromagnetic energy-based activation. In material jetting, it is equivalent to 3D equivalent of inkjet printing, where droplets of materials are deposited. In binder jetting, only liquid bonding agent is deposited to join the powdered materials. In material extrusion, we extrude materials through a die for deposition. In powder bed fusion, thermal energy is selectively fused regions of powder bed. Sheet laminations, sheet layers are bonded to form an object in sheet lamination. In directed energy deposition, focused thermal energy is used to fuse materials as they are being deposited. So these are the brief description about the 7 printing technologies which is currently used in the industry. In this slide, we shall look into the popular 3D printing materials and methods. This graph shows the current share of 3D printing materials. So, though there are a lot of material and 3D printing, a lot of material and 3D methods are being developed. Based on we can group the materials into following 3 categories based on the use. For example, solid thermoplastics, liquid photopolymers, and powders or granules of polymer, metal, and ceramic powders. These will be the major 3 material forms which is used in 3D printing. Then if you look into the printing methods, we shall study more about the following 3 popular 3D printing methods like fused deposition, stereolithography, and laser sintering. These three are most widely used in the industry. We can use multiphysics CAE for 3D printing at material, product, process, and system level. For example, material design for stiffness and manufacturability, product design for multiple CTQs, and manufacturing process simulation, and system level simulation like the whole 3D printer. If we can improve the material, product, or process and system performance, or solving 3D printing problems by trial and error, or just by turning few knobs, you are welcome to do so. If that works, and at a superficial level, but if that works, that's fine. But our focus will be on the physics-based modeling for the technical insight and problem solving for the first-time right product development. Physics-based modeling will be the key driver in our design and problem solving. This slide shows the fused deposition modeling process. Fused deposition material modeling is a material extrusion process used to make thermoplastic parts through heated extrusion die and deposit a material in stands to build the part layer by layer. This is the definition according to ASTM. The right hand side, what you see here is a schematics of a FD 3D printer. The critical components are polymer wire, then we have a XY motion extruder, then heater, and the support bed which can move up and down, plus usual machine and control interface system. This is the typical fused deposition modeling configurations which is used and most popularly used consumer level 3D printer. This slide shows the governing equations of fused deposition modeling, the physics behind fused deposition modeling. The right hand side you see the schematics of the physics of the process involved in fused deposition modeling. The solid polymer wire is pushed by a set of rollers which is driven by DC motor, which act as a plunger to push the wire into the extruder and creates the necessary pressure. The polymer is then melted at the extruder and pushed through the die nozzle. The physics involved in this whole process is governed by thermomechanical phase change plus flow process. In its simplest form, this is a simple pressure flow, Feuchter's flow, which the pressure difference is related to the viscosity eta, the length of the die L, the mass flow rate Q, and the diameter D. So these are the critical parameters in its simplest form. Then second is the viscoelastic material behavior is the key physics involved in FD. The viscosity is a function of temperature and shear rate, which in turn depends on the history of temperature and the shear rate. This is critical effects. This is critical material behavior, which is critical to model effects like a die swell which happens inside this die. Even if you set die extrusion width to say 0.4 mm, the actual product will be deposited at more than 0.5 due to viscoelastic effect. It's important to understand and model this to make the products right. The print resolutions of 3D printed FT part is a function of diameter, die length, pressure, viscosity, and extruder process and material properties. These are the different properties which we can relate to the final 3D printed part using FD process. This slide shows the FD and phase deposition and multiphysics CAE. Multiphysics CAE can be used at various stages of phase deposition modeling. For example, viscoelastic material modeling, process flow, part warpage, residual stress, part performance. Here we show two examples for the die design and material process modeling. The top right shows the simulation results of the extrusion die design. The counterplot shows the effect of pressure and velocity on the effect of die exit angle. So you can see there are many, we did a parametric DOE from a die angle of say about, 5 degree to even up to 90 degree. You can do this effect in a parametric model. But what you see here is the results. So that you can find the optimal die angle for a smooth flow as well as the required pressure difference. And this bottom right shows the optimization results. This is mainly studies the effect of pressure and shear rate of viscoelastic material. This is for a given die geometry and process parameter. This study shows the effect of material property on the performance. Viscoelastic material model is used. The counterplot shows the effect of pressure on shear rate. This pressure induced shear flow. You can look at the die exit, the counterplots. The effect of pressure on shear rate of viscoelastic material is noticeable at the exit. So it's a pressure induced flow highlights on these slides. Next, we move to stereolithographic process, and simplified as ASL. According to ASTM definition, it is in stereolithography, photopolymerization process is used to produce parts from photopolymer materials in a liquid state using one or more lasers to selectively cure to a predetermined thickness and harden the material into a shape layer upon layer. Right side, you see the components of stereolithographic process, stereolithographic equipment apparatus. So what you see here is this involves mainly a photopolymer in a vat, then the laser system and the mirror system for scanning, and for mirror system for scanning the 2D part, then the moving platform to move the part one layer by layer. Here the laser is used to cure the photopolymer in a layer by layer way. That way you can move the whole once this is cured, then we can move the platform one step down. This slide shows the physics involved in the photolithographic process. The key physics involved in stereolithographic process are highlighted here, wherein the laser radiation exposure is critical as the main source. The size, time, and intensity are critical. The critical exposure time is related. The exposure time is related to for a Gaussian laser beam. The critical exposure is related to the exposure, the laser power, the width of the beam, the velocity of scanning speed, and the penetration depth. Based on this, you can calculate the critical laser exposure energy which is required. The next one is the photo initiation. Upon applications of laser energy, these photo initiators split into two or more components. These components has the capacity to link the oligomer and the oligomer and the monomer. That way it can form a cross link of network. This is the Cure process of photopolymerization Cure reaction. This one shows the schematics of the photopolymerization, where you can see this is the photo initiator, oligomer, and this is a monomer, and this is the cross-link. This happens as applications of the laser or electromagnetic source of energy. This chemical reaction is an exothermic reaction process, and the heat transfer due to the Cure and radiation is also critical. Stereolithographic part performance is related to part resolutions required, speed, scanning speed, temperature, and degree of Cure. The degree of Cure is most critical on this, and all this can be modeled. This slide shows the multiphysics CAE of photolithographic process. The photopolymerization process can be modeled using COMSOL chemical reaction modeling model. The laser optics can be modeled using ray tracing or full wave model. Right hand side, what you see is the radiation heating process model simulation results. A typical photopolymer for a given thickness. The scanning of the laser, the way how the laser moves, that also modeled using analytical functions, and the radiation exposure based heat transfer is modeled along with the conduction, convection, and radiation heat transfer. The contour plot shows the temperature built-up. So the temperature built-up in the parts, and also it shows from moving the laser moving from place A to B, the scanning thing. And we can see what is critical here is the temperature built up, also the through thickness temperature built up, because the radiation, the laser absorption is based on Beer's law. So the depth of importance, the depth of heating is critical, because that is the depth which is critical wherein we move the next step. So all this we can model to understand the coupled effect of photopolymerization, laser radiation, and the Cure to model the product performance. In the next 3 slides, we will talk about laser sintering. This technology is very promising for high temperature part fabrications. The last two, whatever we've seen, mostly thermoplastic kind of polymer is used, but this is used for metal, polymer, metal, and ceramics. Laser sintering is a powder bed fusion process used to produce objects from powdered material using one or more lasers to selectively fuse or melt the particles at the surface, layer by layer, in an enclosed inner chamber usually. The right side, what you see here is the components of laser sintering process. The part is built in the powder bed chamber. From the left side, from the powder stack, a powder roller will deposit a single layer of powder stock onto this powder bed. The powder bed is then sintered using the laser. Then once that laser sintering is completed, this is moved by a step, one step down. And the whole process repeated again, like moving the roller and then curing and then moving down. There are two types of laser sintering. One is selective laser sintering, and second is laser melting. As I mentioned earlier, usually polymers, metal, and ceramic powder materials are used in this process. Laser or electron beam is used for sintering. So laser sintering is about sintering fusion or melting, of powder granular material. As shown in the top right, there are two type of granular materials are used. One is solid granules as shown here, and the second one is solid granules coated with a fusible coating. So these are two kind of main forms which is used in laser sintering materials. The schematics of the laser sintering process physics is shown in this. You can see the scan direction, laser beam, and this is the powdered layer bed. Um, you can see powder layer bed. So the key process involved in this are melting and collisions of these particles. Then here you can see, solidified layers already. These are the layers which is getting sintered, and this is one which is in the current. This is how it is built layer by layer. And these are the physics involved in this process. As we mentioned earlier, laser heating, heat transfer, phase change, collisions of the particles. This can be, in the simplest form, we can relate the collisions time T as a function of directly proportional to the viscosity and the diameter of the granular particle, and inversely proportional to the surface tension. Critical are these three for a collisions to take place, and the collision time we can model using these parameters in its simplest form. But we will do much more than with the multiphysics CAE. And the next step will the solidification and the densifications of this for a good quality part. In this slide, you will see the multiphysics CAE of laser sintering. We will see some examples. The laser heating process simulation is similar to what we have shown in the earlier slides. So we are not repeating that again. Two examples of critical process in laser sintering process. One, as I said, is the granular material fusion, which is the collisions of viscous particles due to surface forces. So what you see here is the two viscous particles, and the evolution of or the collisions of these particle simulation results are shown, which we did with the two-phase flow with the level set method. Two particles. Initially, there will be meniscus will form, and due to the viscous and the surface force effects, this will slowly merge into it. Slowly, it will collisions, and it will form into a fused granules. So this simulation is very fundamental for laser sintering process, and by modeling this, we can understand the effect of different forces which contributes to this simple. Other than viscosity and the surface tension, we can look at other process parameter to understand the in-depth about the collision process. The second is the melt transition or melt flow and solidification is the critical process. In the bottom, what you see here is a melt transition modeling results during melt solidification due to temperature gradients. Phase transition by moving boundary interface according to the Stefan's problem as a function of process parameter gradient is shown here. And this is very important to understand the melt or the melt flow due to the laser heating to melt flow and the solidification takes place. And that can be modeled with the same with two-phase flow with the level set or phase field modeling methods. This slide shows about 3D printing and multiphysics CAE. Multiphysics CAE for product design is well known and leveraged successfully for innovative product development to reduce cost and cycle time. That's known. But in this webinar, we focused on the use of multiphysics CAE for 3D printing and process modeling for the first time right product development. We can also use to solve specific problems associated with 3D printing, such as overhand support, warpage and shrinkage, or residual stress, which is mainly associated with the 3D printing process. We'll see more of multiphysics CAE for 3D printed part performance as we move forward. To predict the 3D printed part performance, additive manufactured material property prediction based on its microstructure is the starting point for part performance. We would prefer to have a microstructure as shown on the top right. This is a homogeneous microstructure. This is usually we'll see in top-down kind of process. But we usually, in a 3D printed part, we usually ended up with a microstructure as shown in the bottom. What you see here at the bottom is the typical expected microstructure of the three 3D printing techniques which we considered and its microstructure, expected microstructure. And you also see the micromechanical simulation results as an inset within the microstructure. The bottom left is the microstructure of the fused deposition modeling process. In fused deposition modeling, the product is built using extruded polymer strands, and this is built layer by layer. So in this, you will expect a microstructure as shown in this cartoon. The properties are expected to be transversely isotropic, and X and Z properties will be transverse isotropic, and Y will be different. And the properties in Y long-term directions, as the polymer fibers are getting stretched, you will get better properties. But the transverse properties in X and Z on these materials will be lower. The middle one is a stereolithographic process and its microstructure. You can see this is built using layer by layer of a polymer with the photopolymerization process. So you would expect a transverse isotropic, you would expect a microstructure like this, and the properties will be transverse isotropic. In this case, the properties are inherited from the photopolymer. These photopolymers properties are relatively lower than the thermoplastic, engineering thermoplastic. So you would expect lower mechanical properties compared to other conventional polymers. Laser sintering is this micrograph is the microstructure of a laser sintered 3D printing process. In this case, we use the granules to fuse together. So you would expect, these are ideal microstructure by the way, so you would expect a microstructure something like this. So here, since we fuse the granules, you will expect to get equivalent isotropic properties in all the three directions. But the properties in all the three, compared to the solid material, it will be lower due to porosity. So the whole modeling is to minimize this porosity. But this is the beginning for performance prediction, because the microstructure, the properties of the material which is 3D printed will be different than its original state or the bulk form. So 3D printed part material property will be different. So we need to use this material property to predict the full part performance. So this is the beginning or the starting point for part performance prediction. So far, we have seen engineered products. Engineered macro products. This one, what you see here, it's a molecular level product. A single wall carbon nanotube. Um, Even chemist and biologist, carbon nanotubes, you can't normally visualize without like electron microscope kind of stuff. But the chemist and biologist want to even visualize these molecular models for a touch and feel like what engineers do. So to do this, so this is one example where we took molecular models for 3D printing. So here we need to link the molecular world to the engineering world for 3D printing. The example shows that link. So the carbon nanotube properties were generated using molecular simulation tools. The atomic level properties are collected. This info is used as an input to build a 3D CAD model in COMSOL. This is then used to make STL file 3D printing as shown here. This once it is into a CAD model and it is into a CAE environment, we can use this for other, you can do a CAE simulation to understand the properties, even the macro level properties, and use this to even understand the atomic level properties. At the same time, develop structures which are inspired, ultra lightweight macro materials and structure which are inspired from nano level features. This slide shows the projection about the future of 3D printing. Where are we now? Where it can go, the 3D printing. Most of the current printers print using single materials, either polymers, photopolymers, ceramics, or metals. But we will have, as we move forward, we will have a true multi-material printing capability wherein within one system or one machine you should be able to print with all the materials, polymers, metal, ceramics, even natural materials and biomaterials. Because if you see the good example as a bio machine is you and me. And also if you look at the practical product, an automobile is a good example wherein you use different materials to make the whole product. But that will be, the multi-material will make that as a reality. Right now, if you look at the material world and the electronics world, two different as far as 3D printing is concerned. But these will be fused or integrated together to make truly multifunctional products. For example, your smartphone. So the integration of the semiconductor manufacturing methods or the electronics with the material fabrications will enable us to, print products like your smartphone or electronic devices together. Current products, if you see, all these products are printed at about a meter length scale. That's a maximum size. Mostly it's about 1 feet, but maximum current 3D printers can print in a meter length scale. But that is not the scale where the most of the real world engineering structures are at. So we need printers which we can print at larger scale. For example, printers to print large scale industrial machines or residential home, like printing your home, within 24 hours you should be able to, build your own home, which takes more than 2.5 years with the current production technologies. Similarly, infrastructure, which is the need for infrastructure development is the current need for a country like us. So 3D printing, which can print in a large scale or large size at the same time at the faster speed, will be the next developments. There are some demo projects of this. I'm sure that the future will be with these kind of machines. And also the innovations in nanomaterials, 4D printing, self-assembling systems, all this will enable breakthroughs in 3D printing for phenomenal growth. This webinar is from a2a.com. A2A Scientific, as Ajay mentioned earlier, we are from A2A Scientific Technologies, COMSOL certified consultant. So you can visit a2a.com for more about multiphysics CAE. For CAD, CAE, COM, or 3D printing, you can visit 3d.a2a.com, where you can do more about, you can learn and do more about 3D printing. Also, you can send an email at print@3d.a2a.com for anything more about 3D printing. And thank you.